Good morning, Year 12. Welcome to, well, this is something I hate doing. I'm teaching to an iPad and you're going to be watching this from home. I'm going to be demonstrating an experiment instead of letting you do it, and that is anathema to what I think makes good chemistry. You guys should be doing this experiment yourselves, but unfortunately that's not really an option at the moment. I told you in the email I sent that I'd be doing investigation 6.7, but I am going to mix it up a little bit. There's some things I'll be omitting and some things I'll be adding to investigation 6.7. But in any case, we're looking at the amphiprotic nature of salts. Now, an amphiprotic salt is one that can act as either an acid or a base. And I'm using the Bronsted-Lowry definition here. And I'm saying it can either donate or receive a proton. All right, now you guys, I'm trusting, have read investigation 6.7. And so you know we're going to be dealing with amphiprotic salts. Unfortunately, in the storeroom, I've only got 2 amphiprotic salts, at least from the list in investigation 6.7, and that is sodium hydrogen carbonate and sodium hydrogen phosphate. And the formulae for these are NaHCO3 and Na2HPO4. Phosphorus has a valency of 3. I've mixed those up into 0.1 molar solutions. And you can probably see there's a third beaker. This is just deionized water that Mr. Rose prepared for us. So what I'm going to do is I'm going to add 2 mils of each of these to test tubes. So sodium hydrogen carbonate in these first 2 test tubes. By the way, I should say that I rinsed all these test tubes very carefully before I started, and that's something you guys need to make sure you're in the habit of doing. Okay. Sodium hydrogen phosphate in the next 2. There's 2 mils in each. And deionized water, you'll see why I'm doing that in a minute, in the last 2. Now, I know that that's not the 4 salts that the textbook says, but we're going to work with these 2 salts, the sodium hydrogen phosphate in these 2, and the sodium hydrogen carbonate in these 2, sodium hydrogen phosphate in these 2. But the first thing the textbook asks us to do is to use a pH meter to measure the pH of each of these. Now, amphiprotic salts can act as either an acid or a base. In the case of sodium hydrogen carbonate, when it dissolves, it will release an H+ ion into the water, which makes it an acid. But it's also got a carbonate, so it can take H+ from the water. As you know, the acid and carbonate reaction produces carbon dioxide, a salt and water. And so this one can act as an acid or a base. The sodium hydrogen phosphate behaves in a similar manner. It can act as an acid or a base. And I'd like you, please, in your work on this, to write down the acid and base reactions, or the acid and base dissociations of sodium hydrogen carbonate and sodium hydrogen phosphate. They're both amphiprotic, so they can both donate or accept a proton. So take a moment to do that now. In fact, pause the video rather than me waiting for you, and write down the dissociations, or the proton accepting and the proton donating reactions of sodium hydrogen carbonate and sodium hydrogen phosphate. In fact, I think you can probably see the formula written down there. All right, I'm assuming you've restarted the video now. I'm not going to use a pH meter as per the experiment. In fact, the experiment in discussion says, why could a pH meter not be used? Which is interesting since they've already said to use a pH meter. But I'm going to use universal indicator. 1 drop in each test tube. And let's have a look at those colours. Let's start with the deionized water, which is very clearly yellow, which is pH 6. I'll put that against my white lab coat so perhaps you can see it. And obviously both deionized waters are the same. They're both pH 6 yellow colour. The phosphate is about there, I would say, which is pH 8, which means it's acting slightly basic. And the carbonate looks to be maybe neutral, maybe slightly basic. I'm not sure how well the iPad is going to pick up the colours, but yeah, I'd say it's about 7.5. So, given that these two salts have both gone ever so slightly to the basic side, if I move that, you might be able to see the colours. Given that these two salts have gone ever so slightly to the basic side, I want you to now look at the proton accepting and proton donating reactions you wrote down a moment ago and circle the dominant reaction. All right, next thing to do is to go through the analysis of results in the investigation. And the first thing is determine the concentration of H3O plus, or determine the H plus concentration, same thing, given that we have pH 7.5 and pH 8. Interestingly, the deionized water has given us a pH of 6, so please work out the H plus concentration in those, and I'd like you please to post those concentrations in the discussion on Canvas. Bonus points if you can explain why deionized water has come up with a pH of 6. It's obviously gone a yellowy colour. So what reaction has happened? What's caused it to get a pH of 6 rather than 7, which is where it should be? The next question in analysis of results is list the samples from the lowest pH to the highest pH. Well, that's easy. Water, sodium hydrogen carbonate, sodium hydrogen phosphate. Which sample is the most acidic? Water. Although again, I'd be interested to see if you guys know why the water is ever so slightly acidic. Which sample is the most basic? It's the phosphate. All right, I've done that for you. I'm moving on to the discussion that I can see in the investigation. It says write the reaction with water for each sample. Well, you've already done that if you followed the instructions I gave you. For each sample, decide if the salt solution was an acid or a base. Explain your reasoning. Again, that's pretty obvious. And 3, why could a pH meter not be used for this investigation? I'm not entirely sure, to be honest. Might have something to do with the spectator ions, but I'm not sure. Okay. Conclusion, pretty straightforward. I promised you I would add something to this investigation. What I'm going to do is I'm going to demonstrate the amphiprotic nature of these salts by reacting them with an acid or a base. So what I'm going to do is I'm going to add sorry, excuse me, I'm just going to write this down so you can see what I'm doing. I'm going to add acid and base to each one, just 1 drop each of 0.1 molar hydrochloric acid and sodium hydroxide. And perhaps you'll be able to see what's written down there. So that's what I'm going to add. I'm going to add hydrochloric acid, sodium hydroxide, acid, base to each one. And there's already a drop of indicator in each one, and that will show us what's going on there. Right, so I wonder if that'll balance up there so you can see what's going on. Probably not. Anyway, I'll put it back up in a moment. All right, so I've got some hydrochloric acid, and I'm going to start at this end. I'm going to add it to the water, and we know what's going to happen with the pH colour chart. It should go red because it's acid. And sure enough, that's what's happened. Very clear red colour, pH. Perhaps 3, maybe 4. I'll let you guys decide, but obviously very acidic. And we knew that was going to happen. Likewise, the sodium hydroxide is your classic strong base. I'm going to add 1 drop to this water, and we're expecting it to go to the purple colour. And sure enough, that's what happens. So we've got pH in the order of, I don't know, maybe 10 or 11. Now, amphiprotic salts are interesting because they can act as an acid or a base. And by adding an acid, I'm going to force it to act as a base. So you saw what happened when I added the acid to the water. It turned acidic. No surprises there. What's going to happen to the just off neutral sodium hydrogen carbonate when I add acid? Well, have a look. In fact, I might move that a little closer. Have a look what happens when I add a drop of acid. The answer is absolutely nothing. And the reason is that it has acted like a base. It's accepted that proton, and that's no longer acidic, unlike that, because it's acted as a base and accepted the proton. In fact, I do think we've got a very slight colour change. I think perhaps we've moved a little bit closer to neutral. I'll let you be the judge. Now let's see what happens if we add a base to this amphiprotic sodium hydrogen carbonate. And again, the answer is it has actually gone slightly basic. I'd say that's about pH 9, maybe pH 8. I'm not sure how clear that is for you, but yeah, I'm thinking probably about pH 9, but still nowhere near the pH 11 of the water. And that's because when I added the sodium hydroxide, which is a strong base, it started acting like an acid, and it's donated protons to the sodium hydrogen carbonate. It's the acid. Let me start that sentence again. The sodium hydrogen carbonate has acted like an acid. It's donated its proton to the sodium hydroxide and neutralized it. So we can see the amphiprotic nature demonstrated very clearly when it acts as a base because you add acid, or it acts as an acid when you add base. The sodium hydrogen phosphate will behave in a different way, or slightly different, but it will still demonstrate the amphiprotic nature. So I'm going to add firstly acid to the sodium hydrogen phosphate. I'm hoping you can see the video clear enough to see the drop hitting the liquid in the bottom. And yet again, nothing's happened. So the sodium hydrogen phosphate is acting as a base in this circumstance, and it's neutralizing the acid. Now I'm going to add base to the sodium hydrogen phosphate, add a drop of sodium hydroxide. And this is where we're going to get a slightly different reaction. And that's very clearly gone well over to the basic end. pH probably about the same as the water by the looks of it. And that's because the sodium hydrogen phosphate has only got so much ability to act as an acid. It's donated what protons it can, but obviously that single drop of sodium hydroxide was more than it could cope with. Still, interesting that to start with, it was really close to neutral, or was about the same colour as that, really close to neutral rather than looking like a base, and yet when you add a base, it goes all the way to basic side. Okay, I'll just put the guide up there so you can perhaps pause it if you wish and see which one's which. I've tried to demonstrate the amphiprotic nature of these salts. We've seen that they're all really close to neutral when they're just on their own in 0.1 molar solution. We've discovered that both of the examples we used, the sodium hydrogen carbonate and the sodium hydrogen phosphate, were both close to neutral but both on the basic side. You've written out the reaction with water for each one of those. In fact, you've written out both possible reactions with water to show how they can act as an acid or a base. You've then circled the reaction that is the dominant one out of those two, and we've discovered that they're both slightly basic, so the accepting protons happens at a slightly greater rate than the donating protons. We've then added acid and base to each one and discovered that the sodium hydrogen carbonate can accept and donate protons in response to having acid or base added. We've discovered that the sodium hydrogen phosphate is quite good at accepting protons when the acid is added and able to neutralise it, not so crash hot at donating protons in response to the base being added. That's the end of this lesson. Please post your questions in the Canvas discussion board, and I look forward to, well, I'm not sure if seeing you online is the right way of putting it, but I look forward to interacting with you in the Canvas discussion a little later today. Thanks, Year 12. The last thing I put in the notices is for you guys to let me know how you're going with work rate. I'd really appreciate that if you could let me know. I'm not sure if I'm setting too much work, not enough work. I suspect it's too much at the moment. But if you guys can give me a guide of where I'm up to, that'd be really helpful. I also need to give you some lesson time to work on your homework. But it's one thing to walk around the classroom and see where you're up to. It's another thing to be working remotely where I don't get as much feedback. So if you could let me know in the same Canvas discussion, that'd be really helpful. I hope you guys are getting on well. Stick with it. I'm not sure how long this is going to last, but we'll do our best in the meantime. Cheerio.